All right, so we're going to do this moving blocks activity together. We're starting with the analyze and represent. So we have the situation where you have two blocks connected by a string over a pulley. One block is falling, one block is sitting on the table, and they're both going to be moving together. We're starting with the understand and plan part. So I've already gone ahead and made my list of knowns and unknowns. This is coming from the problem statement. The important thing here is I'm giving everything a label and everything a numerical value. So for my knowns, I know something about the masses of both of my blocks. I know M1 and I know M2. So M1 is my mass of block 1, M2 is my mass of block 2. I also know that M1 is bigger than M2. So when I chose my numerical values, I made sure to choose numerical values that match that. So the mass of block 1 is 4 kilograms, the mass of block 2 is 1 kilogram. Mass 1 is bigger than mass 2. I'm also given a numerical value for how far the blocks move. I know that they move a distance of 0.75 meters. And so I've given this a symbol, L, to represent that distance traveled. So those are my knowns, M1, M2, and L. And what am I looking for? I'm looking for my final speed, VF, of the blocks after they move some distance, L. So I've given that a symbol called V, and I've given it a subscript F equal to question mark because that's the thing I'm looking for. Those are understand and plan part. Now moving on to the assumptions. What are the assumptions that I'm going to make in this problem? So when you're making assumptions in physics, some of them will come from the problem statement, and it's always a good question to ask yourself is always, is this a reasonable assumption to make for this situation? So we're going to start with the ones that are given in the problem statement, which are the first three here. An ideal pulley and an ideal string. So are these reasonable assumptions to make? For the problem, they could be reasonable assumptions to make. Maybe the pulley is relatively small. Maybe you don't have a very massive pulley, in which case you might be concerned about the mass of the pulley. In this case, in the problem statement, it says it is a massless pulley, looks relatively small, so this might be a good assumption to make in this situation. It will also simplify our calculations a little bit, which we'll talk about moving forward. Our next assumption is an ideal string, again, something given in the problem statement. But you could imagine that if I said something different, if I said something like maybe there's a heavy chain connecting the two blocks, and then you might need to take into account the mass of the chain. But barring that, I'm going to assume that we have an ideal string, which will help simplify things a little bit. Maybe you have like a piece of floss that are connecting the two blocks. So an ideal pulley and ideal string are okay assumptions to make, barring any extreme other situation. I'm also told that the surface that mass 1 is sitting on is frictionless. So I have no friction written here. I'm not going to be concerned about friction. Maybe the block is sitting on like a piece of ice or something. So that would be an okay assumption to make. I am also going to assume no air resistance. So I'm not told this in the problem statement, but I'm going to assume no air resistance in this situation. Maybe the blocks are massive enough for air resistance to not cause too much of a problem. And I'm okay with these assumptions also because I know that at the end of the day, when I get an answer, it's going to be for this ideal situation where we have an ideal pulley, an ideal string, no friction, no air resistance. And in the real world, I might get a different answer. And we'll talk about that in the sense making. So I'm sort of going into this problem using these assumptions, knowing that it's not totally representative of the real world. And that's okay, and we'll talk about it in sense making. Another assumption I will make is that we are near Earth. This lets us set g equal to about 10 meters per second squared. That's a good assumption to make. We are usually on Earth running experiments, so it's a good one to make here. And the last assumption that I'm going to make to simplify my calculations is I'm going to assume that they start at rest. So I've written v initial, v sub I is equal to 0. I'm assuming that they start at rest. I could assume that they start with some initial velocity, but for simplicity, I'm going to assume that they start at rest and we don't have to worry about that. So we've got all of that detailed down, and now let's go on to the represent part, which I'm going to solve this problem using forces. And so I'm going to draw free body diagrams. So I'm going to draw two boxes here to represent my blocks. Put one there, put one here. I'm going to label these up here so my diagrams don't get too cluttered. M2. Let's start with M2. So what do I know about M2? It's hanging by this string. We are near Earth, so I know that I should have a gravitational force and a tension force. I'm going to draw my gravitational force like that. There is my gravitational force, my type. Gravitational force is the superscript on block 2 by the Earth. I'm also going to assume that they start moving downwards, or mass 2 will move downwards, mass 1 will move to the right. And so I know that my tension force, the force going upwards, that's pulling, like holding back mass 2, should be smaller than my force of gravity. So I'm going to draw that, something like that. There's my tension force on 2 by the rope. I'm thinking about mass 2. I'm wondering, is there anything else in contact with the block? There's not. I think those are all the forces left on our block. We're good to go. Let's go to mass 1. So mass 1 is sitting on a table, so I know that there should also be a normal force, a gravitational force, and a tension force. I'm going to start with my gravitational force, and because I know that my mass 1 is bigger than mass 2, I'm going to draw an arrow that's bigger than that gravitational force arrow over there. So my gravitational force arrow might look something like this. Here's my gravitational force on 1 by the Earth. Now, because the block isn't moving up or down, there's no acceleration up or down. That means there's no net force up or down. So my normal force from the table on block 1 should be the same magnitude as my gravitational force, but in the opposite direction. So I'm going to try to draw them relatively the same length. So here is my tension force on 1 by the table. All right. Now the last thing I need is my tension force from the rope. So I have an arrow here, F tension on 1 by the rope. Now, because I have an ideal pulley, I know that my tension force around the pulley will stay constant. So these arrows should be relatively the same size because the tension forces there are equal. So even though I've labeled them as different forces, because they are different forces acting on different objects, these two forces are the same magnitude. Okay? All right, so there's our analyze and represent part. Oh, I did forget one thing. We should always make sure to include a little bit of a coordinate system on our blocks, on our free body diagrams. You have some freedom here to choose which direction is positive and negative. I generally like to choose the direction of the acceleration to be positive. It will help simplify things a little bit. It ensures that I don't have to carry around a minus sign. So I'm going to assume that this direction is positive for block 1. And I'm going to assume that this direction is positive for block 2. The downwards direction will be positive. So now I think I'm all set and ready to move on to the calculate part.